So a couple of introductions. I'm here on my own. These are my opinions. They don't reflect my employers. Some of the things that I talk about we may or may not do at work, but again, personal opinions, likely incorrect. A little bit about myself. My official title is network architect. Everybody has different definitions of what an architect is. For me, I still spend my day-to-day logging into network equipment. I do everything from the mundane to the spectacular. I like Python. I love regular expressions. Out of curiosity, does anybody else here love regular expressions? A couple of people. So some good news for everybody who didn't raise their hand. We're not talking about regular expressions today, like at all. This is where I am. And out of curiosity, how many folks are strictly networking people? Okay, systems people? Both works. Developers. Cool, great mix. How many of you have on-premises data centers where you actually have network infrastructure to worry about? And how many in the cloud? Cool, awesome. So I also like to give a brief heads up on what this talk isn't, so you can go find something more interesting. This is not how to do pretty much anything. What it is an exploration of problems specifically in the networking space and what makes them sort of unique to the networking space and new to the people in that space. And it is a very gentle and high-level introduction to continuous integration and continuous deployment practices as they apply specifically to networking. It's a huge topic. Anybody who's spent more than 5 minutes looking at anything related to continuous integration knows this is a massive topic in general. So I'll start a little bit by describing what I view as a misalignment between the way a lot of networking folks, at least that I've met, tend to view things versus what, again, my opinion is the reality. Networks are complex a lot of times. I've worked at multiple places where the network actually was whomever the top level network person, it was their personal CCIE lab. And that's never awesome. They're usually pretty slow to adapt to any changes that are necessary, either from a business perspective or even if it's just something as simple as turning up VLANs. I talked to one person fairly recently who said it's about a three-month process for a one-line ACL change. To me, that's ludicrous. It's a really bad thing, but it's representative of some very typical network environments, especially as they grow larger and larger and larger. There's a great quote here. I won't read it for you. It's up there. But a lot of times, our networks are 100% production. There are not many of us who have the luxury of having a network that is non-production. Usually when we do, it's made up of gear from 10 years ago that we recycled into our lab environment. And you do something in the lab and it works great on this 10-year-old gear running the latest version of software that that switch can run. And then you go put it into production and then you've got your CTO calling you and asking you why everything just went down. And this is a stark contrast to what businesses really require. And this doesn't apply just to networking. This is a general statement of businesses. For networks specifically, they do need transport of services. And at the end of the day, that's what every network, to me, really is. From anything in the business, they do need rapid response. They need agility. They need things to change quickly. 3 months for an ACL change is only delaying the entire application by another 3 months. And it's a compounding effect, because if you don't get that change right the first time, and then you've got another 3 months, even if it's, even if you've got 2-week cycles, If you get that change wrong the first time because you didn't have enough information, or they decided to add some new feature, you're now delaying everything by another 2 weeks every single time. I don't know about the rest of you, but I've frequently received ACL requests that were missing key data, and both sides thought that it was complete. And then they go to run the application, and it turns out the ACL request was not complete. Reliability and stability are key for everything. It doesn't matter what you do. I have yet to meet a network person who has told me that their network did not need to be reliable or available. If you are one of those people, I would really love to talk to you, because that would be super, super interesting to me. We're super behind, too. The system side and the software side, they've been seeing these great, radical new technologies. We've seen things go from really big servers running 50 different applications to virtualization, where you can run servers in half a gig of RAM, all the way down to containers that can eat up maybe 30 to 60 megs of RAM, depending on the size. And networking has not quite made it there yet. This kind of applies specifically to some of the more traditional vendors that are out there, right? Cumulus, you can run a Cumulus VM and 300 to 500 megs of RAM, and you're fine. But you go look at something from Cisco and NXOS, you can get away with 3 to 4 gigs of RAM at a minimum, depending on your feature set. You look at some of the more advanced features where you might actually need data plane support, and you need 8 to 16 gigs of RAM. You look at a virtualized iOS XR box, and you might need as much as 32 gigs of RAM. And beyond just the issue of resources, right, is automation tooling. The systems and application sides have a 5 to 10 year jump on us. I think 2011 or so is when I first became aware. So I know it's been longer than that, right? And my focus is obviously SaltStack, because I'm here. I have all sorts of opinions on some of the other things that are available out there in terms of strictly config management. One of the things that I love about SaltStack is that SaltStack is not config management. It can certainly fulfill that role, but for me, that's like 10 or 15% of why I like Salt. The rest of it is all around the event system. So besides just the technologies, the people that are involved in networking are also behind, as a direct result of the industry in general being behind. A lot of network engineers probably could not even write a bash script to save their lives. And that's not a reflection necessarily on them. If they have had no need to do it, they're not going to know how to do it. Python's been gaining ground, but even still, being able to do more than a couple hundred lines in Python tends to be kind of a difficult match to find. And I alluded to this a little bit earlier, but the way that network engineers, at least in my experience, have viewed their networks has traditionally been on what protocols am I running? How many links do I have? They tend to not focus on the transport of applications and services, and instead tend to get caught up in some of the minutia of protocol configuration, sometimes leading to a great deal more complexity that doesn't really need to be there. My preferred approach is make everything simple. Ensure you can transport an application across your network. Anything else should be considered on an as-needed basis. So in order to kind of take the next step and try and get ourselves to a point where the systems and the applications folks have been for a little bit longer, we have to, again, opinion, look at things as services. Stop trying to think of how do I configure OSPF on this one device, and start looking at your entire OSPF domain as a whole. How do you model this sort of data? What do things look like? What is the full configuration required to completely deploy that particular part of your network? Not from an individual device's perspective. I mean, at some point, you're going to have to get into those details, right? Especially if you have multi-vendor networks, or even if you have one vendor with multiple platforms, and they calculate things like MTU differently between the two platforms. But in general, try to take a step back from where your network is at a device level. In order to do that, the only way you can really accomplish those sorts of things is if you look at things, if you break things down into modular components. Templating an entire configuration in one go without breaking it down doesn't do a whole lot besides just say, yes, we have a standard config that's generally implemented. Modularity is wonderful. Pipelines, something that should absolutely become a part of daily life, and it's the focus of this talk. The vast majority of this talk is on pipelines. So, sorry. A couple of common definitions, just so that we're all thinking along the same lines. These aren't necessarily correct. Everybody has their own opinions on words like DevOps, pipelines, SRE. They all mean 50 different things depending on who you're talking to, what their experiences are. But for the purposes of this talk, these are the definitions we'll be using. This is a really terrible visual representation that I made. I'm not at all creatively inclined. So this is kind of how I view pipelines. A pipeline is a collection of stages that are unidirectional. Inside of a stage, you have one or more jobs. Inside of a job, you have one or more scripts. And these should all be concrete units of work. Nothing like super crazy, like don't try to do everything in one script and call that a pipeline. Like that's not a pipeline, that's a script. This is a visual representation pulled from GitLab's website of a pipeline. Another way to look at exactly what was on the other page. There's a series of stages: build, test, staging, production. Each stage has one or more jobs, and the jobs run in parallel for each individual stage. Excuse me. Network pipelines. So this is software pipeline. Network pipelines are super similar. They're actually exactly the same. That's kind of the beautiful thing. The only difference is what tools you use to accomplish your goals. This is a network pipeline, pulled from a working example. Looks exactly the same as the software one, just, you know, stages have different names, jobs have different names, different number of jobs in certain stages. Concepts are the same. I'm not going to read this to you. It's here for reference, but going line by line by line by line, going to have a bad time. This one specifically is GitLab CI. There's plenty of other CI things out there. If Jenkins is your jam, use Jenkins. I'm not a fan, but that's okay. More, all same file. It's rather long. It's like 100 lines or so, I think, is the total length. But it's really easy to read. If you're here, you're probably familiar with YAML. This is all YAML. Stages and pipelines. Linting is stage one. This is the first place to fail. This is your first opportunity to reject a change. This is one of the most important stages to me. And the reason for that is it provides so much value for so little effort. If you do nothing else, implement a linting stage. The linting stage is there to, first of all, validate syntax where possible. There's some example tools, YAML-lint, XML-lint, JSON-lint, depends on what you're using and what you're doing. If the test fails, it's probably a good point to just stop. Part of pipelines is you're not actually required to fail the entire job if one stage fails, but if one stage fails, probably the rest of them are going to fail. The other part is model validation. There's, again, some example tools, depending on if you're working with YAML or XML or JSON. This one is crucial. If your organization, in the example, says, you know what, all customer VLANs have to have an ID of 3,000 or higher, there's absolutely zero reason a human being should be looking at your configurations during peer review to ensure that you used a VLAN ID of 3,000 or higher. That's insane. Tooling exists to allow you to define models and schemas for those models so that you can validate using a machine much faster than a human can that your VLAN ID is higher than 3,000. If it's not, fail the job. There's all sorts of other places you can apply this to. Autonomous system numbers, OSPF area IDs, anything under the sun that might be a standard for your organization. Get it into a model, write a schema for it, validate your models against your schema, give your humans their time back. Let them do things that are valuable. And perhaps equally importantly, catch things that your humans are going to miss. I don't know about the rest of you, but I don't have every single standard for my network memorized. My memory is not that good. So in normal manual peer review, I'm going to miss silly things all the time. If your BFD timers are supposed to be fixed at specific values, automation should do that for you. It should, at the bare minimum, ensure that those values are the ones that are set. Humans, like I can't stress this enough, that's why I'm spending so much time. Humans are going to miss some of these really simple things so easily, and it's going to make its way into production, and 6 months later, you're going to go, how in the world did this happen? Unit tests. Again, borrowing terms from the software development world. There's lots of ways you can view this. There's lots of ways you can break it down. This is my personal method. Test discrete features on an individual device perspective. Ensure that generated configurations match your expectations. And if possible, do this on a dry run. Do this without involving virtual network devices. With Salt in particular, you can rewrite grain data and trick a Linux VM or a container into thinking it's a different operating system. Well, not really thinking it's a different operating system, but presenting itself to Salt as a different operating system. And you can create your templates based on that and constantly change the grain, constantly regenerate new templates. Doesn't require you to spin up network devices, which is a time-intensive process. Again, this is a stage that should be quick, and you should fail pretty quickly if possible. Again, don't progress. If you have some syntax error that was introduced by creating a new template that you wouldn't have caught in the linting stage for some reason, this is the place that you should try to catch it. The next stage, actually, more information. I won't read all of this. It's more examples of tools. Testinfra is cool because it has direct integrations with SaltStack, so you can write your tests in Python, use testinfra. Life is great. This is an example. I'm not going to go through the code. If you're writing your unit tests in Python, use pytest's parameterization capabilities. Reduces the amount of code that you have to write exponentially. I test for 3 different vendors. I write one function for all 3 vendors. Same thing here. Test for 3 different vendors, one function, and I just pass them in as parameters. And there's the setting of grains, by the way. So each time this test runs, it'll get replaced with the appropriate operating system. This one? Testinfra. So are you familiar with server spec or inspec from the chef kind of world? So testinfra is like a Python equivalent of server spec and inspec, which are written in Ruby. Testinfra supports more than just Salt. If you have mixed tooling use cases, or if you're migrating from one tool to a new tool, for example, if all of your stuff is currently done in Ansible and you're working on migrations to SaltStack, testinfra supports both Ansible and SaltStack. Again, more example. I'm not going to read it. This is really bad code, by the way, so like, don't use it. Write better code, right? Only for example purposes. Once you've gone past the unit test stage, you should have a fairly high degree of confidence that things are going to be okay when they make it to production. But you shouldn't stop there, because let's just say, for the sake of argument, you have some vendor who releases a virtual router and a feature is supported on that virtual router, but it's not supported on the version of code that you're running in production. Not that that ever happens or has happened to me. You're going to have a bad time. Do your integration tests. Get as close to the version of software you're running in production as humanly possible. Some vendors provide virtual routers for every version they release. Unfortunately, some do not. If they don't, just get as close as you can. And if it's something that they don't make publicly available or obvious, go find your SE. There's all kinds of stuff locked behind the doors of your SE that you'll never find publicly discussed. Bug the living daylights out of him or her. And again, this is the point where, like, let's say you're working off the cuff and you're doing some templating work or even working with models directly on the device, and all of your validation from your unit test was right, but for whatever reason, you had an extra space in your validation for, an extra space in your validation on the unit test side, and in production that space isn't there and would cause a syntax error. That's part of the purpose of integration tests. When it comes to integration tests, some example technologies you can use. Vagrant, again, pytest and testinfra. A lot of this is very similar to the unit test stage. The key difference is it's on actual devices. Expect much longer spin-up times at this stage, by the way. Spinning up a VM can take upwards of 10 minutes or more, depending on the platform, the version, how much CPU and RAM you've given. It's a much slower experience than the Linux side. As an aside, Vagrant's not the only option, right? It's an example, but if you have OpenStack at work, you can throw those VMs up using OpenStack. If you have something like EvenG or GNS3, they both have APIs. You can use them to spin up individual routers or to spin up complete topologies depending on what resources you have. I will point out in particular a Vagrant plugin called vagrant-triggers. I have seen some virtualized devices that can't utilize Vagrant's normal provisioning process. Vagrant-triggers kind of lets you get around that a little bit by allowing you to provision after the Vagrant run is complete and running it as a script local on the box, which then SSHs into the VM. For the sake of simplicity, create an extra network, again, if you're using Vagrant, to connect your Salt infrastructure directly to your virtual routers. It makes things much easier to diagnose and troubleshoot if you don't have to worry about connectivity between Salt and your virtual devices. And just shell scripts, pretty easy on a single device. Once you've finished your integration tests, this is, to me, a very cool feature, review environments. have a larger topology if possible. Again, if you can do this with your private OpenStack cloud, or if you have a large, beefy GNS3 or even G box or series of boxes, bring up more complete and complex topologies, deploy your entire environment to it, and have a network engineer log in. Why do that if you're supposed to be catching all of these things before? Well, because you don't know what you don't know, and you're not always going to capture every single bit of thing that you should check via automation. For example, you're deploying BGP, and all of the configs look great, and everybody agrees that the configs look great. And you've mocked out some data, and all of your tests pass, and then you get to deploy it in production, and it doesn't come up because somehow one side had a timer that the other side had different. Review environments make it really easy to catch weird things like that. Review environments make it really easy to break things in some unpredictable and interesting ways. The key, though, once you've found something, make sure it gets back into your tests. Your review environment should not become the new manual review for every single tiny little thing. If you are at that point, there's probably bigger problems. Everything that you test in your review environment, you should make a solid effort to try to get back into your linting, your unit tests, your model validation, your integration tests, whatever it happens to be. I mentioned this already, but Vagrant's not the only way. Lots of tools out there. All of this is great, but this sort of implies that there's a gating mechanism where a human being has to know when something's going into production. And as great as automation is, I am still a fan of having my hands on the keyboard when something gets deployed. If something goes wrong, for whatever reason, something wasn't caught, I want to be there at a moment's notice to be able to check everything. In order to accomplish this, having a solid branching strategy is crucial. In my example, there's 3 branches. One is development. It's essentially a feature branch. It should be short-lived. It's hopefully tied to one engineer's specific changes, and it gets merged into a slightly longer-lived staging branch, where you can get changes from multiple engineers into one place and running. Because what you don't want to happen is 2 engineers working on something in parallel that ultimately have some conflicting parameters, things that would cause an outage in production. Get these into a staging branch, let it live a little longer, let it bake, spin up that review environment, and leave it there. When some other engineer's merging in a new change, get that merged into staging as soon as the sign-off is done, and get it redeployed into staging so you can ensure that all of these changes that are happening in isolation are working well together. Once you are at a point where you feel comfortable that all of these things are working well together, tag it for release, merge it to a production or a master branch, go on about your business. Let the master branch deploy automatically, and I guess I'll step back a bit. Apologies. Part of your staging environment should also be rerunning all of your same tests. Running tests in isolation is great. Running tests for multiple things combined together is even better. And it can be virtual, it can be physical. It depends on what you have available. Take advantage of APIs for things like OpenStack or GNS3 or even G if you have them. When things get to the production environment, that's kind of the point where things can start to go awry. So get an automated system to deploy your changes. Make sure you have hands on the keyboards before it happens, or have a push button where you actually have to say, okay, now go deploy. I'm a network engineer. Reliability is important. Everything runs over the network. I'm a little bit more paranoid. Do this with a schedule. If you have the opportunity and you know you have every Friday a production release for the network at 10 a.m., and all engineers are available and on deck, and you don't have 50 different meetings booked at the same time slot, schedule it for a Friday release at 10. Have post-deployment tests for your network, and more importantly, find a way to integrate with your systems and your applications teams. When you deploy your changes to the network, even if the network looks great, your application could be on fire. As soon as you deploy to production, call in a hook to your application team's post-deployment tests. Whatever they're doing to validate their application is good after they release something, find a way to hook into that and call it. Make sure that you have your finger on the pulse, and you're the one that's going, holy crap, I just deployed some change that's broken the application. Then you can go notify the application folks, and you don't have this 30-minute delay where they say, suddenly we're not receiving messages on Kafka anymore. So this is a lot of talking. It's a lot of information. It's such a huge topic. This is actually the first talk I've ever done that I don't have a demo just because of time. I do have a demo if you're interested. Come find me after the talk. I think I'm fairly close to out of time. So again, just a quick recap of some of the technologies involved in doing this. I didn't mention viral previously, but again, if you have the license for it, it's a potentially decent way to deploy a virtualized network infrastructure if you're a Cisco shop. Pipelines, really, all they are is a series of things, generically. More specifically, they tend to be tests along with potentially some deployment-related tasks. And your stages should start small, be quick, and increasingly become more complex so that you're not spending 2 hours on some tests just to find out that they all failed when it's something that you could have pretty easily caught early on if you had structured things a little bit differently. So fail fast, fail early, fail often, but hopefully not too often, and hopefully not in production. Review environments, I can't stress enough. If you have the ability to do it, do it. Make sure people are logging in. If you encounter something in production that you somehow didn't catch through your pipeline, identify what that thing is, go back to your review environment, and you can spin your review environment up exactly as it would have been deployed in production, and see if you can find in your review environment exactly where things broke down, and then go write a test for it. All of this doesn't do much good if you aren't continually adding test cases. When you branch, protect your production branch. Ensure that nobody can push changes directly to it. The modern hosted Git providers all have a feature to prevent somebody from pushing directly to a specific branch or list of branches. Excuse me. Don't let branches get merged from anywhere besides staging, if you have that luxury. If you don't, it's kind of a non-issue. But if you do have the luxury of having multiple environments, only let things come from one place. So that's pretty much all I've got. I did lots and lots of talking without much pause. So if anybody has any questions, feel free. If not, sure. Of post-production tests? Sure. So are you familiar with Napalm? OK, so Napalm has a system called Napalm Validate. Actually, it might not exactly be called that, but if you Google it, you'll find it. And it has the ability to do things like check to ensure, taking BGP as an example, check to ensure you're receiving greater than 30,000 prefixes. If you're deploying something to an edge internet router and you're getting a full BGP feed, make sure that you've got greater than 700,000 prefixes. And that's kind of a safety guard to ensure that if you're making changes to your BGP policies, you didn't accidentally screw something up horribly and end up dropping half the routes or even all of the routes without realizing it. Does that make sense? Cool. Absolutely. I don't know if Napalm Validate specifically does that, but you can absolutely write some Python to connect some systems together. If you're using some graphing tool that will graph drops or error rates, most of those have some API where you can get the data back. Query the API, determine if you've got some drop rate greater than some threshold that you've decided. You know, if it's 5%, 5%. If it's 1%, 1%. Excellent question. I actually should have talked about that. So the question was, for things that don't have Salt minions natively, how do you get Salt to manage them? So Salt has a thing called a proxy minion. They take about 40 megabytes of RAM, maybe 60, something very, very tiny. You can run many, many, many proxy minions on one server. And those proxy minions are designed to talk to Salt and essentially relay information to a back-end device. So Napalm has proxy minions. Juniper has them, like specifically Juniper. I think Cisco Nexus has specific proxy minions. From Salt's perspective, besides the configuration of the proxy minion itself, it doesn't really know that it's talking to a proxy minion any differently than a standard minion. Yeah, they use proxy minions in order to communicate. But like I said, Salt doesn't really know, from an end user's perspective, Salt doesn't really know it's talking to a proxy minion. In the code, you'll find some proxy minion specific hooks, but otherwise, like from an end user perspective, you're writing states or whatever, Salt itself doesn't really know that it's talking to a proxy minion. Sure. Anybody else? Yes. Sure, so the question was, why use Vagrant instead of using Salt Cloud? Sure, so the quick and short and easy answer is, if you're getting your feet wet with Salt, you may not know much about Salt Cloud. Vagrant's a really easy thing. You can write a bash script and have a Vagrant environment, and you're done. The other part of it is, if you're in a place where your entire environment is not Salt, or where you may not necessarily have the cloud type of infrastructure in your environment, Salt Cloud doesn't provide a tremendous amount of use in those cases, right? Like, Salt Cloud's great if you're able and enabled to spin these things up in AWS or Azure or GCP, or if you operate your own private cloud. But if you don't operate your own private cloud and you can't get the financial sign-off to start spinning up expensive VMs in AWS or GCP, then Vagrant can be a simple low-barrier entry. Or if you want to get started, but you don't necessarily want to bug your systems team or risk accidentally exhausting resources, Vagrant's kind of a safe space. You can do it on your laptop fairly easily without much investment or complexity. Yes? So the question was, have you used Salt to automate firmware updates? No. Definitely something you can do, but there's quite a bit that goes into a software upgrade. from my perspective. Draining links, ensuring that they're drained, making sure that your device is receiving 0 traffic, and then doing the actual upgrade, making sure it's successful, putting traffic back on the links, and ensuring that things are going through your devices as they should. Right, and right, in the back. Yeah, so the question was, can you find out that you're breaking things before you actually break things? And the answer is, it depends. If your organization has a staging environment for the application side, and if you can easily hook into that and deploy changes to that, then yes. Or if your environment is Docker or Kubernetes based, where you can completely virtualize the application stack, then you can pretty easily use either, if you're using libvirt, you can do TCP sockets to connect to interfaces, or UDP. You can use some sort of network socket to connect interfaces, and deploy your changes to your virtualized staging environment, where you also have a virtualized application environment attached, run things through, test, run your post-deploy application tests, and hopefully catch it before it makes it to production. Sure. Anyone else? Yes. Please do. Please do. Great question. So the question is, if you're doing simple things, what are the advantages of Salt versus Ansible? And it depends. If your organization's already using SaltStack, standardize on tooling. If they're already using Ansible, there's probably an argument to be made to standardize on tooling and use Ansible. That said, there are things about Ansible that drive me nuts. Flow control in Ansible is the dumbest thing I have ever seen. If you need to conditionally run a task, you have to know which YAML key you have to define. You can't use Jinja in an Ansible playbook. One of the, just from a pure config management perspective, 0 advanced features, one of the things that I love about Salt is the fact that it's Jinja 2, or insert templating language here, right, if you want to use something other than Jinja 2, but it's that templating language everywhere. If you need to conditionally run a particular state, it's Jinja 2. You don't have to learn some special when. If you need to loop through something, you're already writing Jinja 2 for your network templates. Writing it for controlling state execution, to me, is a very pleasant experience compared to Ansible, which has like 4, 5, 6 different ways to loop through something based on what your data structure is and what things you're trying to get out of it. Anybody else? Cool. Appreciate everybody coming by. And like I said, there is a demo if anybody's interested. Just come find me afterward. Thanks, everyone.